Okay. We left off an example 3.
Back right there.
Get our notes out and let's go.
Everyone's gonna be here for another.
We were talking about basically models of real life. Exponential growth and decay is what we're mostly working with. We'll do a couple logistic growth today. And then we'll look at one on our graphing calculator of like a bell curve example. Yes. Yeah. Remind me I gotta change it then. All right.
Yes, I'm sorry.
It's okay. It's.
No, I don't.
So here's another real life example of exponential, in this case, decay. You can see it's titled radioactive decay. We're talking about isotopes. So I mentioned yesterday, you might have seen these like in chemistry before, but you basically have like material that kind of like disintegrates over time, and it's can be modeled like exponentially. So we have 2 example problems we're going to do here. Kind of set up differently where you have to find the missing value, similar to what you have to do in your homework here. Don't worry too much. Obviously, this is just telling you like what type of isotope it is, and those have to do something with like the number of protons and neutrons and all that good stuff. But we only have to worry about the math part of this exponential growth, the model. Okay, so the half-life is basically the time it takes for like the amount to cut in half, is what that refers to. So we know the initial quantity here is 10 grams, and we know it takes 1,599 years for that to cut in half. That's what that means. And some like isotopes disintegrate like way faster than others. Like some, I think potassium is either really long or really short. I can't remember. I'm not a chemistry teacher, but this one's obviously pretty long, right? Let's start with our model and then just kind of piece in what we know. So here's that little exponential model that would work for both growth and decay. We know our initial quantity is 10 grams. You guys remember what letter that is? A. Good. Yep, so this is A. Our initial amount is A. Is 10. Okay, so eventually I want to figure out the amount after 1,000 years. But this is kind of giving me an ordered pair. It's telling me that I know after 1,599 years, my quantity or my amount of this isotope will be cut in half. So how many grams would I have? 5. Yeah, exactly. So it's kind of giving you a point, cut in half. Half of 10. So now we can solve for B. And since we're talking about radioactive decay, what type of number should we get for B? A negative number, right? We should be getting a negative because this is exponential decay. Let's go ahead and solve this. I would divide both sides by 10. Natural log of both sides. Okay, and then you just take the natural log of 1/2, divide it by that 1,599. And I usually just round to 4 decimal places. You'll see, I'm not going to do this in my calculator because we did a ton of examples yesterday. Negative 0.0004. So here would be my model. Let's write it over here. Y equals 10 is my initial amount. E to the negative, and you can just do 4 decimal places here when you're writing model. X. Okay. Now to answer the question or to find the missing value, I want to figure out the amount of material we have here of this isotope after 1,000 years. Yes, sir?
So like when I type that in my calculator, it comes up like it's like -4, just writing 3 and then E like -4. How do you like?
So that's scientific notation.
Yeah.
So what was it? 4 point.
Yeah, it's -4.3 and then like a bunch of other numbers. And
Yep.
then E is -1. So it just means we're 3 4 places a lot.
Yep.
Oh.
Yep. Yes, good question. Sorry, I forgot that does that. Yep, scientific notation. Now keep that exact. I mean, I have my graph pulled up so I can do it quick. Keep that exact value in your calculator because we're gonna need it. So here's what he's talking about. That's just scientific notation, so you move it forward to the last. That's a 0.0004. Negative, I should say. Keep that exact because we're gonna use it to answer this question. How would I use my model here to find the amount after 1,000 years? Where would I plug that 1,000 into? X. Good. Yep. $1,000. Okay, so remember I showed you then if you have to like have a follow-up question using your model. So now we have that exact decimal. We can times that by 1,000. So I want to do e to that power. So you can hit this button, second answer. It'll feed that in there.
What one did you do? Sorry.
Or what one?
Like, for your answer.
So you can just hit, if you have this, what was that number? 1599. If you just do times, it'll like feed the answer. Yep, so you don't have to hit a button for that one. Times 1,000.
How can you do 1,000 and 10,000? Isn't it 4 spots that you move it?
Well, we're multiplying by.
It says
Yes.
the amount after
I
1,000
thought you
years.
were like,
Yeah.
I don't know.
Oh, you thought I was putting it in decimal form?
Yeah.
Okay, yeah. Now I'm doing this follow-up question. Times it by 1,000, and then you're gonna do e, and then second answer, e to that power. And you could type in 10 e to that power, or you could do this and then times it by 10. Times by that initial amount. I mean, you could do that one step too. It's really good to know how to use your calculator, so feel free to, stop me and ask questions because this is important to know how to punch all this stuff in. Okay, so we'll just go 4 decimal places, so about 6.4824 ... grams. Which that answer makes sense, right? Because we know that after 1,599 years, it'd be cut in half at 5. So it makes sense that around 1,000, we're not quite cut in half yet. But we're pretty close to it. 6.4824 ... grams. Okay, so that was to answer the actual question. So here, my whole work up to here was just finding the model, and then that helped me find the amount after 1,000 years. All right, this next one's a little trickier because we don't know the initial quantity. We don't know A. But don't worry, it's not a substitution one. There's a little simpler way to set it up. I do this because... Okay, so we're going to start again with our model. So we don't know A, and we obviously don't know B. But we do know the half-life, and we know how much there is after 1,000 years. So let's start with plugging in our half-life. Okay. So we know whatever A is, our initial amount, we are going to have half of that, half of A, after 5,715 years. Okay, does that make sense? Now the reason why this is nice, again, we don't know what this is, but we know that essentially I'm plugging in my half-life. I'll have half of that initial amount after this many years. Now what actually ends up happening to our A's in our model here? They kind of cancel out and we'll be left with something that we can solve for B. Okay, and then we'll use that to figure out A. So if you want to write in your notes, like we could technically divide both sides by A. We get half equals e to the 5715b. So we're left with one variable. We can solve this with natural log. That cancels. So I got B, 2B. Let me see. Another pretty small value, which makes sense because these are decaying very slowly. So that rate is really small. This one might have given it to you in scientific notation again, probably.
Yeah.
Okay.
Do you want us to write like that, or can I just write what our calculator says?
I would do 4 decimal places. Yeah. You wouldn't typically see like scientific notation written within a model. Okay, so here's what we know now, folks. We still don't know A, but we know our B. And in this step, Brianna, you can just round to 4. You don't have to do the dot, dot, dot. All right, now I could use this piece of information. This is kind of like giving me a point on this graph. It's telling me that after 1,000 years, I have 2 grams. So I could plug in 2 for my time, 1,000 grams, and then I could solve for A. And that's all we need to do. We're trying to find A, right? This is our initial amount. So after 1,000 years, now I'm kind of essentially plugging in this point. Oh, sorry, I put that in the wrong spot. After 1,000 years, years goes with the variable. Sorry for taking notes this time. After 1,000 years, we have 2 grams left. Okay, good catch. I didn't solve that whole thing with the wrong number. Okay, so now this one actually isn't too hard to solve for A. We'll evaluate this number, and then we'll take 2 divided by that. So, I mean, you can do that all in your calculator, but you could also times this by 1,000. That's not hard to do. Okay. So I would just do, well, you could either multiply these first or negative 0.0. Oh, wait, we want to use that exact answer though, don't we?
Yeah.
Okay, good catch. So I got to do the natural log of 1/2 divided by 5715. Okay, there's that exact one. Yeah, we should use our calculator for this. So we want to do E. I would use parentheses to the power of that answer. That'll feed in that exact decimal times my year was 1,000. So I get that number. Okay. So that's what this number is. So we're going to do 2 divided by that mess. Two divided by second answer. Nice, we got the right answer. 2.2578 dot dot dot. These aren't like, how do I want to phrase this? The numbers are just kind of nasty, right? That's what makes it look so complicated, but like actually doing the like solving part, like the algebra, isn't too bad. It's just you kind of get some like nasty numbers and you want to try to be as exact as you can when we have these real life problems. Okay, so to answer their question, the initial quantity then would have been this grams. We could write the model if we wanted to. It doesn't ask us to. We just had to find the initial amount. Okay. I like those problems. Good old radioactive decay, math in real life. Don't say I'll never use this in real life. All right, now we're just going to do 2 more. So one of them is an example of the next one, logistic growth model, where we have like a capacity, and you can see like the equation is very similar to this equation where we have like e to a negative exponent like in our denominator here. So you would never have to come up with these models yourself. The only ones I'll expect you to come up with like on the test next Tuesday are like exponential growth and decay. Similar to like this, I just gave you like points on the graph. Or, something like this. We came up with that model ourselves. Exponential growth and decay. You would never be expected to come up with this equation. Just apply it. Okay, let's try one. The state game released 100 animals. Yes, question?
How do they just come up with the equations?
I mean, they model it in real life. There's ways to use your computer to come up with these models.
It's crazy. It's the part.
Yeah.
You just have to be trying.
It is crazy. I mean, we came up with these ones ourselves. It's using algebra. But yeah, there's ways to model pretty much any kind of data you want. I've never algebraically had to come up with something like that. I'm guessing that's probably something more you'd have to use a computer for. So yeah, but it's cool because no real life data is perfect, but there's a lot of different types of functions that can be used to model real life data. Exponential growth is very common. Logarithmic growth isn't super common.
Did you
Linear
quizzes
growth.
yesterday?
Yeah, I did. Okay, let's try this one. The state game released 100 animals. They believe carrying capacity is 1,200 animals, and the growth can be modeled by the function below. How long will it take the herd to reach, oops, I was supposed to say one half, not on half, one half of the preserve's carrying capacity? Okay, so P of T is representing our number of animals here. So if our capacity is 1,200, and we're trying to figure out how long, so we don't know the time, that's what we're trying to solve for, the herd to reach half of our carrying capacity. So what's half of 1,200? 600, so we're going to plug 600 in for our population here of animals. And we're going to algebraically solve this for T. 8, 8. Okay. This looks a little nastier than it is, but yes, you can either think of this as cross multiplying, or I'd multiply both sides by this whole thing. So I'm just going to kind of do that. Multiply by our denominator, so we're going to get 600 times 1 plus 8 e to the negative 0.1588 t equals 1,200. Now I want to distribute that 600. What could we do instead to get rid of it? Yeah, divide it off. Picture this, you're just taking off the layers around t. Could you distribute the 600? Yeah, you could. You're just going to make some extra steps. I don't know if that's the right way to think of it, but just a little bit bigger numbers. Let's just divide that off right away. So we have 1 plus 8e to the negative. What type of equation is this? Exponential. My variable's in the exponent spot. Good. So I know eventually I'm going to have to use logs, and obviously with our models here, they're all base E because that's what's used to model real life data. So we're using a lot of natural logs. Okay, what layer would I take off next? -1. Good. See, this looks scarier than it is. It's not bad. What layer would I take off next? Divide the 8. Good. What layer would I take off next? Yes, take off the base E by doing natural log. I'm just going to write it in like this because we've done a ton of these. Okay, I'll get rid of that. And then divide, you betcha. Okay, here's what I got. 13.1.
I did not get 13.
You're looking for times 5, that's times backwards. Double. Double.
Natural log of 1/8 divided by negative
I think you're right, Mr.
0.15.
Oh, why did I write 1?
Yeah, you're right.
They're careful.
You're always right.
How does it not?
Because the natural log of 1/8 is negative. Yeah, think of this. Natural log curves, they have that point right here. And then we have a vertical asymptote here. So the natural log of anything, like basically smaller, is negative. Because, I mean, this is asking you e to what power would give you 1/8. So that's going to be a negative exponent. Yeah.
Makes sense.
Yeah. Math checks out. Yes, sir.
So rounding directly to 13.1, is that because we want to work with the more like easy, like because you're not gonna say, oh, it takes 13.094, like.
Yeah, this is time.
Okay.
I mean, you could do 4 decimal places if you wanted to. I don't know why I did 1. Usually with time, I maybe just do like 1. I can't remember where I took this problem from, but the units are months, and it doesn't say it in the problem.
Yeah, let's do that.
Oh,
And I don't remember why it was months, but just put months.
Math.
It doesn't say it in the problem.
Math, that's why.
So do we just want to like round like by like what we think is correct?
I'll tell you on the. I just made the test, and I was very specific, like round to here, round to here. On the test, I'll tell you.
So
what.
it says rounding 4.
Yeah.
So it's okay.
Usually my general rule is 4. Obviously when you're doing money, I just do nearest penny. Sometimes when I'm doing, I think on the year ones, I set around to the nearest tenth for years. I don't know why I do that. I just have weird things. Okay, you're gonna need your graphing calculator for this one. Look at that function. Don't worry, you'll never have to come up with that on your own. This is cool, guys. The SAT mathematics score for U.S. high school graduates in 2019. This is real life data. Because your textbooks are really new. So they have this real life data.
Also, at the end of the 8-9 lunch, meet with all students in grades 8 and 9. So that'll be at the end of their lunch. They may be a minute or two late to their 6th period classes. I'll meet with students in grades 10 through 12 at the beginning of RTI for just a few moments today. And we'll get them to RTI. Thank you.
Okay, so we're just gonna put this in our graphing calculator and just look at this a little bit. It's kind of cool. It shapes up that bell curve that I was talking about. That is often used. Actually, really fun. Quick fact. Right now I'm taking a grad school class about what's it called? Assessment. It's assessment for like guidance counseling. So about how you like assess students and but they talk a lot about like scaling and scoring, and we just got done talking about the bell curve. The math teacher in me was like, oh my gosh, I love all these numbers. I had to do like a worksheet last night where there's a bunch of scores and I did a bunch of statistics on it, and I was like, I love this.
Yay.
So yeah. Anyways. It reminds me of this. Okay, we're going to type this into our Y1. Now, everybody do this with me because there's lots going on here. We got to be very deliberate with all of these parentheses. Okay.
I didn't put one of those.
We're going to start with 0.0034. This isn't too bad. Second, hit ln so it does e to the x. Okay, we're going to wrap this whole exponent in parentheses. So parentheses, and then you're just going to essentially copy exactly what is on your paper.
So do we just distribute that in?
No,
negative?
no, we're going to do this. Negative, parentheses, we're going to type it exactly like this. X minus 528, parentheses, squared.
Too fast.
Divided by.
I got a straight line, right?
You guys, it's showing you my key press history. You can always look right.
Yeah.
I can't read that.
I know.
You should know this.
Come on.
Divided by 27,378. All I did here is I just added in an extra set of parentheses to my full exponent.
Make sure that negative.
Hold on, we gotta fix our window.
Oh.
Yeah, I was just gonna
Yeah,
ask
just
about
a
that.
straight line as of right now.
Yeah.
Because you didn't follow directions correctly.
Look at. So look at the range here. It's saying that X, which X is representing the actual score, ranges from 200 to 800, so you can't score lower than a 200 on the SAT. I've never taken the SAT, so I'm not quite sure how it's scored. So we're going to do our window for X from 200 to 800. And then for Y, I want you to go from 0 to 0.004.
What's the scale by?
Oh.
Okay, guys, I'll show you.
The scale by 1?
200. Yeah, I just kept it as 1.
Dang.
Right.
To 800.
Jasper and 8.
0 to 0.004. You can keep this scale. So
That is beautiful.
Table.
that should form like that bell shape curve. Isn't it satisfying?
800.
Woo!
801.
Okay,
Why does it keep going?
Why is mine never working?
we'll go back to the window.
The average 528.
Who is it? Let me see it.
I don't know what
Yeah,
it is.
but-
I'm so bad.
Are you sick of us?
I need a break.
Or has it just been a long week?
You don't
I
have
need to
anything
move
in your
because-
y equals. It's blank.
I don't know.
I think I need to
Then
move
I
because
typed
we
it
made
in
this
the calculator
Oh, she's typing in like the regular.
If only there was a copy and paste button.
What the heck? I hate that thing.
Oh, you guys.
What did you do? Why do you
Okay.
I don't know.
Oh,
He's struggling over here. He is a power.
Well, no,
Okay.
it's supposed to be a power.
No, it's not.
Listen,
Could delete.
figure it out.
You got him.
All right, now it says.
Whoa!
Did it work? Isn't it satisfying?
Yeah. But I don't.
Do you get it?
Yeah, he's just not.
Just wait.
Thanks, Jackson.
I did.
Wow. Oh, thanks, Connor.
I just stood there.
Okay,
Literally, these chairs are
now
up and down, up and down.
let's just quick sketch this. So it forms that cool bell-shaped curve, right? Like this. All right, now to answer your question, and we're gonna find this exactly. But if I want to estimate the average, do you guys remember what point on the graph is the average, Bailey? The max. Yep, this point right here tells you the average or the mean. That's the same thing as average. So draw this in your notes. That highest point is where the average scores are. So it's saying that 50% of the scores are more than that, and 50% of the scores are less than that. Now I know it's plotting the scores on the x-axis. Okay, so you're like, wait a minute, why are the scores like lower? These are the scores, right? So these scores are getting higher. Okay, and then they're just telling you like, I guess more what percent of the people. So 50% of the people scored higher than that. 50% scored lower than that. These we call like standard deviations, how far you are away from the mean. Don't worry about that. But just know that this point right here, that's obviously right in the middle. That's how I calculate your class averages. You know, 50% are higher than that, 50% are lower. All right, do you guys remember how to use your graphing calculator to calculate that exact point?
Yes, I do.
Calc max.
Second,
Yes.
Calc
Maximum.
maximum.
Oh yeah, I knew.
Maximum, not Maximus.
Second Calc.
Oh, let's go.
All right, so left bound, you just have to put enter a point to the left of the max. Right bound,
528. I got it.
That's what I got.
guess
I got
528.
Yes.
Wow.
I am a
527.
Why is mine so off?
Get it.
That sucks.
Oh, really?
No,
No, go back.
Mine 528.0000000.
Wait, how do you get out of it? Okay.
Because you
Because
didn't
you
get
did
it
it wrong.
exact.
That's
Well, you did it for me.
Yeah. No, I didn't. Yeah, oh, I did.
I got it.
So go last.
Stop.
Okay, so to answer this question, because X is representing the actual score,
528.
use the max feature.
I got 528.0033.
We got the average score for the math SAT was about 528. That's Good.
What'd you get?
I didn't
Oh,
take an
you
SAT.
said
I don't even know what the
What'd you get on the
SAT is.
ACT?
100%.
On,
Yo, she cheated.
I think I got a 25 on my ACT.
Yeah.
I got really low in reading and English,
Yeah,
really,
that's no
and
different.
really high in math and science.
I got decent in math, terrible in reading.
All right, we don't need to talk about it. And I will say, I'm not trying to.
I got like 5.
That's it for notes.
Not trying to take the AC